Hi everybody, my name is Colin DeGraf. I'm a postdoc at Carnegie Mellon University, and today I'll be talking about supermassive black hole mergers in cosmological simulations, specifically looking at host galaxy morphology and high-redshift mergers. To give you a brief overview, I'll start by discussing the morphologies of galaxies where supermassive black hole mergers occur. To tie in with that, I'll discuss the importance of incorporating the merger timescales in terms of understanding the galaxy morphologies and also general populations of black hole mergers. And then I will show some results from a brand new simulation looking at very high redshift mergers and incorporating low seed masses and dynamical friction modeling. So before getting into the galaxy morphologies, I just want to point out that the galaxies which host supermassive black holes do tend to be typical mass galaxies. So here I've shown with contours the typical black hole mass, stellar mass scaling relation, and then with colored points showing the galaxies which are hosting a supermassive black hole merger, color-coded by those more detectable by LISA or by pulsar timing arrays. So we can see that these merging black holes are found in typical mass galaxies. But just because they're found in typical mass galaxies doesn't mean that their morphologies are standard. So if we look at the galaxies hosting these mergers, we can actually see that they tend to have disturbed morphologies. So here I've got a montage of merger hosts at redshift 2 and redshift 0.5. And in each case, we can see a wide range of morphologies, but in general, we're quite frequently seeing galaxies which are not relaxed. So these galaxies show evidence of having undergone a recent merger. We can see this same sort of behavior if we look at individual cases. So here is one galaxy from the Illustris simulation where each panel is at a different snapshot. And so in the early panels before the black hole merger, you can see a relatively relaxed galaxy. And then especially starting in the top right panel, which is the first snapshot after the black hole merger, we see a very disturbed galaxy, and it takes several hundred megayears before the galaxy starts to be visibly relaxed. Here's another example. This is from the TNG simulation, where again, the galaxy is initially relaxed. Around when the black hole merger occurs, we see a morphology that shows evidence of a recent galaxy merger, and it takes several hundred megayears before we start returning to a nice relaxed state. So, we put out a paper this year looking at this in a very statistical standpoint. I don't have time to go into all of the details, but here I'm showing an S parameter, which is a combination of the Gini parameter and the M20 parameter, to quantify how much the morphology looks like a merging galaxy. So a positive S value suggests it's a merging galaxy. And on the y-axis, we show the time since the most recent black hole merger. And what we see is recent black hole mergers seem to be high S parameters and thus a recent galaxy merger, especially in the red points here, which represent major high mass black hole mergers. So we actually see that we can expect a disturbed morphology in the hosts of these black hole mergers, but that would only survive for a few hundred megayears. Now, that timescale is a bit problematic because in the Illustris simulation, that is what this figure shows, the black hole is sort of repositioned towards the center of the galaxy, so it will merge too quickly. And this suggests that it's really important to try and do an accurate measurement of how long we expect these mergers to take. Otherwise, we're going to make the wrong assumptions on what the host galaxies should look like, which will impact multi-messenger astrophysics. So one way to address this is to actually post-process the simulation, where you can estimate how long a given black hole should take to reach the center of a black hole using dynamical friction. So I've had some students who've done that, and in addition they look at what the growth of each black hole should be during that delay time, and then they recompute the entire black hole merger population. So here I've shown how important that can be. So you can see the expected merger rate going from green for the original simulation down to orange if you include a time delay, and then down to blue if you limit it only to those mergers which should be detectable by LISA. And so we see that incorporating these delays has an impact that could be as strong as an order of magnitude. So it's very crucial that we really incorporate all of these. We've got a couple papers on this subject that you can take a look at shortly. Another way of doing this, which is the ideal way, though computationally expensive, is to run a simulation which actually directly includes these timescales. So here I'll discuss some results from the new Asterix simulation, which is a high redshift simulation. It will be run to lower redshift, but that's still going at the moment, which directly includes dynamical friction. So for more discussion of that, you can see the talk by Nyanyi Chen. For the moment, I'll just work on the assumption that we have dynamical friction in this simulation. Another big change for this simulation is instead of using a single seed mass, when black holes are put into the simulation, they're inserted at a range of seed masses, following a power law between 10 to the 4.5 and 10 to the 5.5 H-inverse solar masses. So we actually have a wide range of low mass black holes that you don't typically find in similar volume simulations. So the first thing to look at is just the black hole mass function, so we can understand what sort of black hole populations we have. So here we're looking at the redshift 5 mass function, and in red is Asterix, and in blue is the TNG 300 simulation. You can see above 10 to the 6 solar masses, there is very good agreement between the two. We can also see some features from the seed mass, the seed prescription. So in TNG 300, they're seeded at about 10 to the 6, and so you see a big spike there. Whereas in Asterix, where it's seeded according to a power law, we actually have a range of seeds, and then a smoother distribution as we go up to higher masses. And if we look at higher redshifts, here you've got redshift 6 and 7 plotted as well, and you can see that again, the two simulations have pretty good agreement. So, given those mass functions, we can also look at what the expected merger rates are. So here I've plotted the rate at which we would observe mergers from the Earth. And so you can see the Illustris and TNG simulations have pretty close agreement to each other, but the Asterix simulation in red has a dramatically higher, almost an order of magnitude higher merger rate. But of course this makes sense because there are a lot of low mass black holes in Asterix which are not resolved or not included in the Illustris and TNG runs. So we can take the Asterix simulation and actually limit ourselves to only consider the mergers which would be resolved in Illustris or TNG. And in the dashed line here, we can see that relation and see that in fact, Asterix actually has fewer mergers than the TNG simulations when you're considering equivalent masses. And we expect this to happen because the dynamical friction model included in Asterix means that it will take longer for the black holes to reach the center of galaxies where the mergers can take place. So this infall time is actually slowing down the overall merger rate, as we expected from the post-processing analysis I'd already mentioned. So the other thing we can do is consider what sort of merger distribution we have in terms of merging masses. So here these solid lines are just back to the redshift 5 mass function, same as what I showed before. But in the dashed lines here, I'm now showing the merging mass function. So instead of the mass function of all black holes at redshift 5, this is the mass function of merging black holes around redshift 5. And so we can again see relatively similar relation between Asterix and TNG, at least at any given mass, though we can see that TNG has more mergers compared to the mass function than Asterix does. So we can sort of combine those two pieces of information to characterize the expected number of mergers per gigayear that a given black hole would undergo, which I show here. So again, Asterix extends to much lower masses than TNG does, but once you're above 10 to the 6 or so, and so that both simulations are well above their seed masses, we actually find relatively comparable merger rates. But this is somewhat coincidental because Asterix goes to much lower merging masses. So again, we want to consider if we restrict ourselves only to the mergers that would be resolved in both simulations, we can see that in this dashed line, where in fact Asterix has an order of magnitude fewer mergers than TNG had. So again, this dynamical friction is really slowing down the rate at which we're bringing black holes together, and so we end up with far fewer mergers involved. So the last thing I want to mention is what this means for detectability of mergers with LISA. So one thing we can look at is the mergers from the TNG 300 simulation. This is only the mergers above redshift 4.7, so that I can do a direct comparison to Asterix. You can see we have quite a few mergers that would be detectable by LISA, tending towards the low redshift rate of any given redshift range that we consider. If we can compare this to Asterix, again, only considering the mergers that are resolved with TNG, we see far fewer mergers, as we've seen in the previous panels. But if we don't limit ourselves to this high mass scale where TNG includes the black holes as well, and we actually have all of the Asterix mergers, we see that we fill in much more of the LISA sensitivity range. So we have a lot more mergers that we would expect to see once you start including these low masses. And in fact, we're suggesting here that we should be getting quite a few mergers, and that LISA should be able to detect some mergers even going up to very high redshift. They'll be very rare, but it should be detectable. So this is sort of emphasizing how important it is with these simulations that we really need to include very low masses, otherwise we're only catching a very small subset of what LISA should be able to detect. And so in conclusion, we've sort of shown that black hole mergers do correlate with the morphology of the galaxies they're in, but that correlation has a limited window that it survives. And so it makes it very important to accurately model the time frame involved in merging black holes. Then using the Asterix simulation, I showed how that dynamical friction modeled directly in the simulation does indeed slow down merger rates and decrease the expected number of mergers we would find. However, by including much lower masses than you would typically find in simulations of those volumes, we actually find that we're able to span much more of the range of what LISA should be able to detect, and we have quite a few mergers that we're able to see in these simulations. So we've got a lot more results from Asterix. You can see some of the other talks about the Asterix simulations. We'll have some papers coming out shortly, and if anyone has any questions on any of this or would like to discuss future work, please let me know. I'll be very happy to discuss it with you. Thank you very much.